In this lesson, you will learn about right triangle similarity, specifically as it applies to right triangles. The objective is to find and use relationships in similar right triangles. So the first theorem that we have has to do with an altitude. So remember, an altitude is a segment that goes from a vertex of a triangle perpendicular to the opposite side. So in this particular instance, we're looking at the altitude that's going from the vertex where the right angle is of the right triangle to that's perpendicular to the opposite side, and the opposite side of the right angle of a right triangle is always the hypotenuse. So we're looking at that segment that's going from vertex C perpendicular to the opposite side, which gives you segment CD. This altitude to the hypotenuse of the right triangle divides the triangle into two triangles that are similar to the original triangle. The original triangle is ABC, and they're also similar to each other. So that altitude divided that right triangle into a small triangle that's on the left, that's ADC, and then there's a larger triangle on the right that's BDC. So those two triangles are similar to each other, and each of them are similar to the original the large triangle, which is ABC. So let's write some similarity statements to clarify this. We have triangle ABC, which is the large original triangle, is similar to triangle ACD. So if you see where they have redrawn the smaller triangle down below on the left, that'll help you see that. Those two are similar. Triangle ABC is also similar to the triangle that's on the right inside, which is CBD. And again, they have drawn that down below on the right to show that. And then these two triangles on the inside, the small one on the inside, which was triangle ACD, it's also similar to triangle CBD. So those are the relationships that you have within that right triangle. Or I could have also stated this to say, instead of three separate similarity statements, I could make one similarity statement saying that triangle ABC is similar to triangle ACD, which is similar to triangle CBD. Okay? Now you have to be sure that you get these in the correct order. The order does matter in this. So let's look at the way that I usually do this is I name my first triangle, name the large triangle, and wherever your right angle is, your right angle in that large triangle is C. That's where the right angle in the other two triangles also has to be. In the triangle on the left, the D, down here at angle D, D is your right angle, so it has to be in the same position in the name as the right angle of the first one. And in the triangle on the right, it's also angle D in that triangle, and it has to be. So all of those have to be in that same position, corresponding position in your name. So if you look at the other angles, so the angle A in the big triangle has to correspond in position to angle A in the one on the left, ACD. And so that leaves, in that particular triangle, that leaves angle B to correspond to angle C in that one. So that's why you've got your other position, the middle one, the B and the C, are corresponding in those positions. If you look over at the triangle on the right, it with the large triangle, the angle that's shared in it is the B angle. So if you go back to looking at the name of the first one, the B in the original triangle has to correspond to the position, that same position in that name for that triangle CBD. They have to go together in the same location. So that's how you can name these triangles and get them in the correct position, is by looking at their corresponding positions. They have to be in the same position in the name. The next definition that we have is for a geometric mean. Now we've already learned that the means positions of a proportion are the positions, if you look at a proportion, it's going to be the denominator of the ratio or fraction that's on the left and the numerator of the fraction that's on the right. Those are the means positions. So a geometric mean, when you have a geometric mean, those two numbers are the same number or the same variable. So by definition, the geometric mean of any two positive numbers a and b is the positive number x, such that a over x equals x over b. Or if you cross multiply those, x times x is x squared, and a times b is ab. And then if you take the square root of both sides of that, you would get x is equal to the square root of ab. So that's just the definition of a geometric mean. So looking at that in a right triangle that we just looked at above, where you have an altitude drawn from the right angle to the hypotenuse, that's going to give you that segment, that's the altitude, is going to be the geometric mean between the two segments QS and SR that the altitude divides the hypotenuse into. So that's our next, so that's going to lead into our next corollary to this theorem. The next corollary is going to state that the length of the altitude to the hypotenuse of a right triangle is going to be the geometric mean of the lengths of the segments of the hypotenuse. So that's just what we stated above in this diagram. The length of the altitude is going to be the geometric mean between the lengths of the segments that it divides the hypotenuse into. So if you look at the diagram just below this, the altitude is in red and the length of it is 4. So the 4 goes in the positions, in the means positions of your proportion. And then the other two segments into which the altitude divides the hypotenuse into are 2 and 8. And they go into these other two positions that are the extremes positions. And if you did cross multiply these, you would get 16 is equal to 16, to see that you've got that set up correctly. In the corollary to this theorem, it states that the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the original triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse that's adjacent to the leg. So let's look at that carefully here. Here we have, you still have a altitude that's dividing that right triangle's hypotenuse into two parts. But here we're going to look at the length of one of the legs, the length of one of the legs of that original large right triangle. That is going to be the geometric mean. So we put that in the means positions, and it's going to be the geometric mean between the whole hypotenuse, which is 4, and the length of the hypotenuse that's adjacent to that leg, which is 1. So here we have, if we cross multiply, 4 equals 4. So we can see that one is set up correctly. Let's use these in the problems on the right, and that will help you understand them. In problem 1, you're supposed to write the similarity statement relating the 3 triangles in the diagram. Of course, your first triangle we're going to name is the large triangle. Okay, the large triangle, and we'll call it EAK. And so we need to set up a similarity statement with the 2 triangles that it divides the large triangle into. So we have a triangle on the, you have a smaller triangle out of this. Let's look at this smaller triangle, this one. In the smaller triangle, your right angle is at the G. And in your larger triangle, your right angle was at the A. So that means I have to put the G, because that's the other right angle in the small triangle. I have to put it in the same position of the name as the right angle in the first one. Then we have angle E is shared between that large triangle and that smaller triangle. So the E has to be in the same place in these 2 names. E has to be in first position because that's where I put it in the other one. And then that leaves the A to finish out naming that smaller red triangle. So now let's look at the other triangle on the other side. Let's look at where's the right angle in that triangle. Once again, the right angle is at the G in that triangle. So we have to put it at the same place as the right angle in the other triangles, which is in the middle. It's where we had the right triangle, or the right angle. So we're going to put in problem 2, you're finding a geometric mean, and the problem just asks what is the geometric mean of 5 and 2. So there's 2 different ways you could set this up. You could set it up as a proportion. We want to know the geometric mean. So if we set up a proportion and we put our variable that we want to find, x, in the means positions, and you're going to put the other 2 numbers, 5 and 12, in the extremes positions. So if you cross multiply these, you're going to get x squared is equal to 60, and x is the square root of 60, and you need to leave this in the simplest radical form. So what is a perfect square that is a factor of 60 It's 4 times 15. I can take the square root of the 4 out of the radical as 2, because the square root of 4 is 2. Leave the 15 under the radical, and that's my simplified radical form. Or I could have taken that definition of a geometric mean that we have over on the right that just says the geometric mean of any two positive numbers a and b is the positive number x, such that x is the square root of the product of those two numbers. So I could have just immediately said that x is the square root of the product of 5 and 12. And that's a little shorter, if you can remember this, to do this, that it's the product, that it's the square root of the product of the two numbers. Then you can go directly to the square root of 60 and finish that out. That's 4 times 15, which is 2 times the square root of 15. Either way, you're going to get the same answer, that x is 2 times the square root of 15. Problem 3 is using one of the geometric means theorems, where we have to find the value of x and the value of y. And we have an altitude, we have a right triangle, we have an altitude drawn to the hypotenuse. So it's dividing the triangle. We know that our geometric means theorems applies. We need to know the length of the entire hypotenuse to put into the formula. So 12 plus 16 is 28. And we're going to need that information, because let's look at x first. X, the length of that leg of the original larger right triangle, it's going to be the geometric mean between the entire length of the hypotenuse, which we just said was 28, and the segment of the hypotenuse that's adjacent to that leg, which is 16. So that's how you've got it. That's how you've got to set it up. Then cross multiply to solve this. It's 448. X is the square root of 448, because you take the square root of both sides. 448 is 64 times 7. So the square root of 64 is 8. I can take the 8 outside of the radical, leave the 7 under, and that's going to be my value for x. Now if you look at y, y is over on the other side, and that's the other leg of that larger original right triangle. So it's going to be the geometric mean, so put it in the means position, between the length of the entire hypotenuse, which is 28, and the segment of the hypotenuse that's adjacent to that leg, which is 12. So that's how you set up your proportion. Cross multiply. Y squared is 336. Take the square root of both sides. 336 is 16 times 21. So I can take the square root of the 16 out as 4, leave the 21 under the radical sign, and that's your simplified radical answer. Y is equal to 4 times the square root of 21. In the last problem, you're finding a distance across a kite. It says Maggie has a kite with the dimensions shown below. What is the width of the kite? Now, there's a property of a kite that we haven't gone over yet, and you need to know that in a kite, that these diagonals are, it divides this diagonal into congruent parts. So that's, and so we need to know x plus x. It wants to know the width of the kite. So you have to look first at these lengths that we have here in this large triangle. Okay, so let's look at this triangle on the one side first. You have a right triangle, you have an altitude drawn perpendicular to the hypotenuse, and you have one part of that hypotenuse is 11 and the other part of that hypotenuse is 25. So just looking at the purple triangle, x, that altitude, the length of the altitude, is going to be the geometric mean between the two segments that it divides the hypotenuse into, the 11 and the 25. That was our first corollary that we had. So if you multiply this out, you got x squared is 275. Take the square root of both sides. X is the square root of 275. 275 is 25 times 11. And I can take the square root of 25, which is 5, out of the radical sign, leave the 11 under the radical sign. So that gives me half of the width of the kite. So my width of the kite is equal to 2x. So it's 2 times the 5 times the square root of 11, which is 10 times the square root of 11, is the width of the kite in simplified radical form.